be too many on these though. Like I said, this is the most important section of the whole semester. This is where you want to ace everything.
Chapter 28.
Chapter 28 for sure. And it's nice to know to be done for 26 as well. All right, let's take a look at column number 11. What is the rate at which thermal energy is generated in the 30 ohm resistor shunt? Variable battery. We want to find the rate at which thermal energy is generated, so we're looking for power. Looking for power. So we want to find either power equals I squared R in that 30 ohm resistor, or power equals voltage squared over R, voltage across that 30 ohm resistor. So I want one of those two. So I need to find either the current through that resistor or the voltage across it. What should I do? Simplify the circuit. So 10 and the 5 are in series and the 30 is in parallel with that. In other words, even though you just told me exactly what I need to do, I'm going to rewrite the circuit just so it's a little clearer what we're dealing with. Basically the same circuit. Just bend some wire, some superconducting wire, and basically the same circuit. So this series combination is 15 ohms, and then we got 15 ohms in parallel with 30. So R parallel is 30 times 15 over 30 plus 15, 450. 45, 10 ohms. So this circuit is looking like this. And now we have a series combination of the 10 and 5. And so our final circuit our equivalent is 15 ohms. Alright, pretty nice. And in fact, I can find the current coming out of the battery. Let's go ahead and do that. Current coming out of the battery will be the voltage of the battery divided by R equivalent. So 30 divided by 15. 2 amps coming out of the battery. And that 2 amps is coming out of the battery in any representation I wish. 2 amps here, there's 2 amps here, it's coming out of the battery here, 2 amps, and out of the battery here, 2 amps. The problem is when it reaches this junction here, it splits into these 2 other branches right here. So if we want to find specifically what the current was through that 30 ohm resistor, one thing we could use would be current division. We use current division, and we've got these 2 parallel split into a fractional amount, and the fraction that goes to the 30 ohms will be the opposite resistance over the sum of the two, that fraction times the current coming into that junction. So actually, lesser of the current is going to go through 30 ohms. 1/3 of the current is going to go through 30 ohms. But if we write like this, current through the 30 ohms is going to be the opposite resistor, 15, over 30 plus 15 times the current coming in. That's going to be 1/3 times 2 amps, 2/3 amps. That's what's going through this, and the rest of it, the 4/3 amps will be going through the other branch, the split. But we only want to know that current. So now the power through the 30 ohms is the current through the 30 ohms squared times that resistance. So that'll be 2/3 amps squared times 30 ohms. 4/9 times 30. Good, right? 4/9 times 30. Watts. What do you think?
Wouldn't that would have been easier to do voltage division right there, and then because it's parallel and has the same voltage?
Glad you mentioned it, Nathan. Yes, it might have been easier not to have gone this step. This is a nice basic approach in general, right? But if you recognize it here, you could do voltage division. And voltage division means that if you have resistors in series and you have voltage across it, each will grab its fair share of the voltage. So by looking at this, there will be 20 volts across this and 10 volts across this. This will grab 2/3 of that 30 volts. So, and that's between these 2 points. And that's the same 2 points as these 2 points. We call them nodes. So there's the same 2 nodes in the circuit. So that means there's 20 volts between those 2 points. There's 20 volts across a 30 ohm resistor. Things in parallel have the same voltage, and they have the same voltage as their equivalent device, in this case, resistor. So the voltage across that 30 ohm resistor is indeed 20 volts. And so the power, which is the voltage across the 30 ohm resistor squared over the resistance, would be 20 squared over 30. Either way works. And in fact, you could also use that voltage rule, or the loop current rule that we did for in general for the 2 battery circuits. You could use that on this too. And in fact, I'm only going to do it once because it's probably more work than it should be. So let's go ahead and do it that way and see what we come up with. So we're going to look at this circuit in a different way. And we're going to apply it using the techniques that we introduced last time, which is the cookbook method, which is mark the batteries first. We only have 1 here. Right? Then assume current directions for all your branches. Right? So I'm going to assume in this branch I've got I1 coming like that. And very likely, since I1 has the only battery, that is the largest current. And into that branch and it'll split into two currents. So let's call this I2 and this I3. So at this point, I1 will split into I2 and I3, and for that matter, those two currents will combine down here. I2 is coming in like this, I3 is coming in like this, I1 is coming down. So essentially, I1 will equal I2 plus I3. Current 1 will equal current 2 plus current 3. At least with the assumed direction that I have here. What would be my next step? Assign plus and minus to all the resistors. Plus minus here, plus minus here, plus minus here. Wherever the current goes into the resistor is the plus. Wherever the current in that branch comes out of the resistor is the negative. We wish to find I2 so that we can apply the power formula. So we want to find I2, which is the middle branch. So I'm going to choose, I actually have three general loops that I can choose, or I can choose any loop that gets me back to the starting point, but three general loops. Which loops should I choose in order to solve for I2? The left and the right. I want to choose the loops that actually have I2 in them. So I can choose the left loop so I can get current I1 in terms of I2. I can choose the right loop so I can get current I3 in terms of I2. So we'll do that. So if I do the left loop, I will have, I'm going to start here. I'll have a negative 30 plus 30 I2 plus 5 I1 equals 0. So we want I1 in terms of I2, so we have I1, 5 I1 is equal to 30 minus 30 I2. Or I1 is equal to 6 minus 6 I2. We're going to do the right loop. So we have right loop. Start anywhere. I think I'll just start right there. Go around this right loop back to where I started. So I'll have a negative 30 I2 plus 15 I3 equals 0. So 15 I3 equals 30 I2, or I3 equal to 2 I2. Now we know that I1 is equal to I2 plus I3. So we have 6 minus 6 I2 is equal to I2 plus 2 I2. So we have 6 is equal to 9 I2. I2 is equal to 6 ninths, 2/3 amps. Squared R, 2/3 squared times 30. I'm just doing that in my head, 13.383 watts. Actually, that wasn't too bad. So if you don't like these other techniques, you can use this cookbook method even on circuits like this.
18.
We can do that one. We haven't done anything from 22, 23, 24 page, right?
24.
Yeah, let's do 24. Well, before we do 24, let's do 22 or 23. Which one?
22.
All right, 22. Take a look at 22. Yeah. What's the potential difference? BB minus BA for the circuit shown. Pinhole battery here. Pinhole resistor. 30-volt battery here. Pinhole resistor. So we want to find VB minus VA. Well, I'm going to approach it in the same way. I want to find the current so that I can actually walk my way from B to A and find the voltage. So first thing I'm going to do is mark batteries and assume current directions. So I'm going to go with the orientation of this battery and say that I1 is actually going like this, along with that battery. And then I'm going to go with the orientation of this middle branch here and say that I2 is going like that. Really, on one of these, I should have just assumed the wrong current direction to see what happens. But not yet. Okay. Because 30 volts is bigger than 10 volts, I'm going to guess that I2, I may be wrong, but I'm going to guess that I2 is a larger current. It's being dominated. So I have a large current and a smaller current coming out of this junction. So what's my assumption for I3? What direction would it be going? To the right. Yeah, it'd be coming out of this junction, kind of like this. In other words, I3 is coming around like this. In other words, I need something to supplement I1 to equal I2. I2 is going into the junction. I1 and I3 are going out of the junction. So I can say that I2 equals I1 plus I3. The current flowing into that junction equals the current flowing out of that junction. So far, so good. Now, I'm going to mark my resistors. Positive, negative, positive, negative, positive, negative. Or everywhere where the assumed currents are going in, positive. Everywhere where they're coming out, negative. Or what I've assumed. I want to find my currents. And maybe just find one current first. So, for lack of a better reason, let's find I1. Right? And so let's find I2 and I3 in terms of I1. So which loops would I choose in order to do that? Left and the big one. The outer one. So I'm going to choose the left loop and the outer loop. Sounds good. So we do the start here, and we'll walk our way around here. I'm just going to go clockwise. I'll have plus 10, minus 10 I1, plus 30, minus 10 I2, equals 0. Just walk my way. Plus 10 minus 10 I1 plus 30 minus 10 I2 equals 0. So I have 10 I2 is equal to 40 minus 10 I1, or I2 equal to 4 minus I1. Look at the outer loop. Start at the same spot. Just walk my way all the way around this way. So I'll have plus 10 minus 10 I1 plus 20 I3 equals 0. Just walk all the way around this outer loop. Solve for I3. 20 I3 is equal to 10 I1 minus 10, or I3 is equal to 0.5 I1 minus 0.5. That's right. So now I have I2 in terms of I1, and I have current I3 in terms of I1. I'm going to plug into this. And since I2 equals I1 plus I3, then it's true that 4 minus I1 is equal to I1 plus 0.5 I1 minus 1.5. Substituting in for I2 and I3, solving for I1. So I'll have 4.5 2.5 I1. So I1 is equal to 4.5 divided by 2.5. 9 divided by 5. So that calculation in my head, 1.8 amps. I had a voice in my head just kind of tell me what the answer was. So 1.8 amps, that's what's going through I1. Let's find the other currents just for fun. I2 is 4 minus I1. So I2 is 4 minus 1.8, or 2.2 amps. And I3 is 0.5 times 1.8 minus 0.5. So that would be 0.9 minus 0.5, or 0.4 amps. And it makes sense. I1 plus I3 equals I2. But we want to find voltage VB minus VA. So let's walk our way from B to A. VB minus VA. We're going to walk from B to A, and how we get there doesn't matter. So if we walk this way, it'll be plus 10 minus 10 I1. That's going to be 10 minus 10 times 1.8. 10 minus 18, or negative 8 volts. Suppose I didn't want to walk that way. Suppose I walked this way. If I walk this way, I would have VB minus VA is equal to I2 minus 30. That would be 10 times 2.2 minus 30, 22 minus 30, negative 8 volts. But 2 paths diverged in the wood, and I took the one less traveled by. That's made all the difference. So, I come to this fork in the woods, and I decide to take the one less traveled by. I go this way. So, if I go that way, B to A, I didn't know I do that. Oh. I'm going to walk here, and I have a negative 20 I3. That's going to be negative 20 times 0.4 is negative 8 volts. How I get from B to A doesn't matter. Just walk my way from B to A. Add voltages and subtract voltages along the way. But this is where you need to be consistent. Once you've applied your current directions and marked your resistors accordingly, stick with it. And if for some reason you assume the wrong current direction somewhere, and one of these currents came up negative, just keep it as negative. So that when you, for instance, are walking from B to A, and if you had a negative 20 I3, and I3 happened to be negative, and that would be a negative 20 times the negative current, whatever that may be. You just keep everything marked the way you don't change anything. Just keep everything marked the way that you have it, and come up with your answers based on what you've come up with. All right? Saying that a current is a negative current and you've indicated one direction is fine. It's just a negative current in that direction. You would get the right answer. Either way, as long as you're consistent and you don't change things midstream. Exactly. Even if you guess wrong, you're still right. Just don't second guess yourself. Look at number 24. In the figure, if I is equal to 30 milliamps, determine the magnitude and sense, which is the direction, of the current in a 500 ohm resistor. 30 volt battery here. 500 ohm resistor up here. 15 volt battery here. 10 volts over here. Some unknown resistor here. 400 ohms down here. And we're told that this current here is 30 milliamps. And we want to find the magnitude and sense direction of the current in the 500 ohm resistor. 3 batteries. One resistor that we don't know, but we are given one of the currents. Well, let's take a look at this. Let's mark our batteries. Positive, negative, and the long and short bars. Let's assume current directions, and probably, since each branch actually has a battery, let's go with the direction of the batteries. Let's say that I1 is going like this, and I2 is going like this. going into that junction equals the current coming out of that junction. But we actually know what I3 is. And we want to find I1. We want to find out what is I1. Now we've assumed a direction, but they want you to give an actual answer as to what the direction of this current is. But we've assumed this direction. Let's see what happens. But if I already know what I3 is, what I could do on this one, you just do the outer loop, the big loop. If I do the outer loop, I'll get I1 in terms of I3. Don't even think about this middle branch. So I'm just going to do the outer loop. I'm going to start here. Oh, I did mark my resistance. All right. So I'm going to do that outer loop. I'll have negative 30 plus 500 I1 minus 10 plus 400 I3 equals 0. Solve this for I1. We have 500 I1 is equal to 40 minus 400 I3. So that means that 500 I1 is equal to 40 minus 400 times 30 milliamps. 30 milliamps is 0.03 amps. That's going to be 40 minus 12, 28. So I1 will equal 28/500, which I could write as 56 thousandths, or 0.056 amps. 56 milliamps. So my answer is either A or B. 56 milliamps left to right, or 56 milliamps right to left. But I assumed left to right, and I got a positive answer. That means I assumed correctly. It's moving left to right. That's my answer. That's for A. That wasn't too bad. Any of this game fun? Is that too much to ask? At 8 in the morning? Oh, man. I'll charge you out. Yeah, Ohio State moved up. Which is, USC won by 69 points. And they moved down. They moved one ranking down. And Oklahoma State won 62 points. They scored 62 points. They moved 2 places down. Didn't score enough points. Ohio State didn't play and they moved up. What do you think? Anything else look interesting? says if I is equal to 0.5 amps in the current segment shown, what's the potential difference VB minus VA? So I is equal to 0.5 amps. Well, our current direction has actually been chosen for us. And so let's go with that current direction and mark our resistors. So this current is going like this, coming in here, coming out here, in here, out here. And we want to know VB minus VA. Well, VB minus VA would be from B to A. We'll walk our way and add and subtract voltages. So as I walk from B to A, I have plus 16I plus 15 plus 10I. It's going to be way too easy. So that's going to be 16 times 0.5 plus 15 plus 10 times 0.5. That's going to be 8 plus 15, 23 plus 5 is 28. Answer. Put a few of those on the test.
Yeah.
What's 28?
Take a look at 28. Current in the 4 ohm resistor is 1.4 amps. What's the magnitude of the potential difference VA minus VB? This is not going to be so easy. Let's see. Current in the 4 ohm resistor is 1.4 amps. What's the magnitude of the potential difference? VA minus. They didn't really say which way the current was going, but they're only asking for the magnitude. So we'll just assume that's going the way that I've assumed. Okay, so since this current is flowing in this branch, it's really flowing around this branch like this. And so with that direction of this current, I can mark these resistors plus negative like that. And in fact, the voltage between this point and this point, looking at this branch only, let me go ahead and put letters on this. Let's call this C and D here. Let's call this E and F here. E and F are actually the same. But just to look at it. So the voltage between E and F is equal to 8I plus 4I. So it's going to be 12I, or 12 times 1.4, which would be 16.8 volts. So there's 16.8 volts between these That means, since things in parallel have the same voltage, there are 16.8 volts across the 16 ohm resistor. In other words, right here is 16.8 volts between those 2 points. So since there's 16.8 volts across that resistor, I can find the current going through that resistor. The current through that 16 ohm resistor is its voltage over its resistance. Which is 16.8 divided by 16, which would be 1.05 amps. So there is 1.05 amps coming down this way through that resistor. Well, at this junction E, I've got 1.4 amps coming out into the outer branch, 1.05 amps coming straight down through that branch between E and F. So there is 2.45 amps coming out of this junction, which means there must be 2.45 amps coming into the junction. So right here, there is 2.45 amps coming into this junction, splitting into those two currents. So I have 2.45 amps going through this 2 ohm resistor up here. Let's mark that resistor. And so the voltage across that 2 ohm resistor up there on top is, by Ohm's law, current times resistance, 2.45 amps times 2 ohms, which would be 4.9 volts. There is 4.9 volts between those 2 points. So if I were going from C to D, I could go this way. I could say 4.9 volts plus 16.8 volts, and I'm there. So the voltage from C to D 4.9 plus 16.8 or 21.7 volts. That's voltage between this point and this point. Let's mark it. 21.7 volts between those 2 points right there. Well, if there's 21.7 volts across that 2 ohms, I could find out the current through that 2 ohm resistor. The current in that 2 ohm resistor is its voltage divided by its resistance. 21.7 divided by 2 is 10.85 amps. There is 10.85 amps coming down through that resistor right there. It's not going to get really messy. But if we look at that junction C, let's rewrite it a little bit here. I've got 2.45 amps going this way. I have 10.85 amps going that way, out of that junction. So the current going into that junction must equal the sum of those two. What goes into a junction should equal what's coming out of the junction. So the current coming in over here should be 13.3 amps. So that equals that plus that. That means I have 13.3 amps going through this 2 ohm resistor on top here. Let's mark that resistor. So that voltage across that resistance by Ohm's law, voltage across that 2 ohm resistor will be current current times resistance, 13.3 times 2, or 26.6 volts. So there is 26.6 volts between point A and point C. We want to find the magnitude of the voltage between A and B. So if I were to walk from A to B any way I wish, I'll walk from A to C and then C to D, and then I'll get there. Then I would say the voltage between A and B would equal 26.6 volts plus 21.7 volts. And I'm there. That is 48.3 volts. So that is VA minus VB. Is it what? Made up for the easy problem, yes. But it's straightforward. This is kind of like the problem that we did, where we had that big network and we had to find the current in the 12 ohm resistor, and it was in the middle of the network. We had to kind of work our way using Ohm's law, and things in parallel have the same voltage, and things in series have the same current, and that sort of thing. So it's that kind of problem. Could I have used loop currents on this one? The answer is yes, but there are a lot of branches to deal with on this one. And if I could assume like a battery over here, and I just want to find the voltage of the battery. But then I'd have a loop current there, one here, one here, one here, and one here. I'd end up with a lot involved there. So actually this is probably best. I wish I had made the diagram larger so I could fit everything that I'm working on there. RC circuits you are having in lab, and we are going to analyze RL circuits in lecture when we get there. So, for the purposes of focusing on what is truly important at this moment, we are going to skip RC circuit section here. And we're going to go on to chapter 29. And when we get to RL circuits, we'll talk about RC circuits. Should I do that? Maybe I shouldn't do that. This is a taped class, right? I should tape RC circuits. But I want to go on to 29 so we can add it on the next test. So I will cover RC circuits. We'll just do it at a different time. I won't take it separate. This is a taped class. I can say, Buckeyes are #1 again? That's great. It seems like they're always #1. Go Buckeyes.
Is that fantasy football?
Is that fantasy football? believe the Minnesota Gophers are number 2 too. That's unbelievable. And then fields. We are going to venture into the realm of magnetic fields, which is kind of interesting. And slight detour from circuits, except that we need to understand magnetic fields so we can understand AC circuits. So it's not too much of a detour. Applications of magnetic fields. Large electromagnets, if we put in a current, there's a magnetic field associated with a moving charge in the current, and hence you can create a magnetic field and use that large electromagnetic field to lift heavy loads. Motors, meters, speakers, all this involves magnetic induction, changing a electrical signal to a magnetic signal into a mechanical signal. So anytime you can cause movement in the sense of motors or meters or deflection, you're changing the magnetic field to a mechanical motion. Recording media, magnetic fields are used to create an impression on recording media, which can be reproduced. So you create this impression, and then you can read it later on by altering a magnetic field using the impression and enhancing the sense for storing video and sound. Digital sense. Computer memory and recording materials, same sort of thing. Being able to store information and then regain it back by reverse operation. Magnetic resonance imaging. What you could do for a human tissue is put the human being inside a very large magnetic field. And hence, you would basically orient whatever small magnetic domains are present in the cells according to that large magnetic field. So you put them in a large magnetic field, and you kind of orient all your magnetic domains in one direction. And then you give it a little smaller magnetic field in the transverse direction, in the perpendicular direction. So you oscillate those oriented domains that are already, preferentially directed. You oscillate them with a transverse magnetic field, and when they oscillate, they'll give off a signal, and that signal can be read as an external signal, and you can basically see the tissue without having to be invasive into that tissue. MRI, incredible technique, and it's getting better and better, and one of the advances in the next 10 years is how good this is going to be, where you can actually see inside the human body without having to use surgery and invasive techniques. Magnetism is related to electricity. They go hand in hand. If you change something, you get the other. In other words, if you move electric charge, if you have electricity, if you move electric charge, you create a magnetic field. And if you move a magnetic field, you change the magnetic field, you create an electric field. So they go hand in hand. In fact, in light, they're always changing, and one changes, it creates the other. Light is an electromagnetic wave. So if you change one, you get the other. They go hand in hand. In fact, in a theoretical sense, and in physics, they're related. Think of it as one force, electromagnetic force. Well, we can set up magnetic fields, and one thing we would notice is that if we had what we call a magnet, which would be in this sense, a device that seems to create a magnetic field. It would have an orientation where on one side there would be magnetic field lines coming out, and then on the other side there would be magnetic field lines coming in. So we would say that the magnetic field lines would emanate, come out of the North Pole, and terminate or come into the South Pole of the magnet. Now, if we had two magnets close together, we would find that they would probably want to orient themselves as shown, such that the magnetic field lines from one magnet emanate down the North Pole would terminate on the South Pole of the other magnet, and not vice versa. So these lines would just create a field, not crossing any lines, and they would go into the South Pole here, orient themselves. What would happen? Every magnet has a north and south pole. And every single magnet you see has a north and south pole. For every north pole, there's a south pole. There are no known monopoles. Making that statement, here's my question. What happens if I came in with a really sharp scissors and I cut this magnet in two, so that I would isolate the North Pole from the South Pole? Would I not do that?
It would create two North Poles.
It would create two magnets. All right? So with this really nice scissors, I cut it in two, and at the place where I cut it, this magnet would end up with the South Pole there, and that magnet would end up with the North Pole there. So I'd end up with two magnets, both with the North and South Pole. So where I cut it, it just split into the North and South Pole right there. But I'm not done. So I said, okay, all right, that was a pretty big magnet. I cut it, turned it into two magnets. This is really sharp scissors. So I'm going to cut both of those magnets, or just cut one of those magnets into two. Cut that into two, so I can isolate the North Pole and the South Pole. Sound good? Create two more magnets. North Pole with South Pole, North Pole with South Pole. So I just keep on cutting. Right? Take every little piece, cut it in two, break it down, North Pole, South Pole, cut another one, break down North Pole, South Pole. Keep on cutting. At some point, you would think, I might get to the point where I keep on cutting, and I'll actually cut them into a monopole on either side, a North Pole and a South Pole. Not going to happen. So even if I cut and cut and cut and cut, I'll always create two new magnets, North and South. I can't isolate one pole by itself. There are no known monopoles in nature. But there are people looking for it. There is a whole division of physics where people are getting funded. They're probably teaching, but they're probably doing research, and they're looking for monopoles. So when they come in at 8 a.m. on Monday morning, they say, I think I'm going to look for monopoles today. I'm going to look over there, in that corner. No monopoles here. All right, I'm done for the day. Give me my stipend. No, I mean, there's a little bit more involved than that, but they're looking for monopoles because they're trying to find something unique about nature. And that's part of what science is, looking for the cutting edge, things that are unique in nature. And if they found it, they'd be famous because they would disprove a long-standing idea that there are no monopoles. It would change the way you look at them.
Would it be an advantage or no?
Probably would be an advantage. If you had monopoles, you probably could use that to your advantage to create magnetic fields and for recording. You have probably make them faster. And, of course, there are no monopoles, but it would probably probably would be a advantage to that. So that's probably where some of the funding comes from. But if that is your intention, if that is your career goal, please let me discourage you from that right now. Because that would really be boring. I mean, you might make a lot of money, but it would really be boring to live from the Earth is a magnet. The Earth has a lot of swirling molten iron and metal material in its outer core, and because of that swirling material over the course of 24 hours, the Earth spins. Earth actually has a significant magnetic field, which is important for life as we know it. It protects us from the sun's dangerous energetic particles, and it protects us from the galactic energetic particles, otherwise we'd be fried. Right? So this is one of those amazing things that allow us to exist. The Earth's north magnetic pole is located close to the south geographic pole right now, and the Earth's south magnetic pole is located close to the north geographic pole of the Earth right now. So the Earth is kind of a reverse magnet according to the way we look at the pole. So that if you had a compass, the north pole of your compass would be attracted to the south pole of the Earth, and vice versa. So the compass would align north-south as the north pole of your compass is looking at the south pole of the Earth. Actually, we might have something like this. In Alabama, the declination, the angle between true north and your compass direction is about 5 degrees east. So if you had a compass, a good compass, you'd only be about 5 degrees off from true north if you're using a compass for a direction. You didn't have GPS. I think I would invest in GPS, but if you had a trusty compass, you'd only be 5 degrees off. Until the poles reverse. Here's a little history. Hans Christian Ørsted lived from 1777 to 1851, found that electric current in a wire deflected a nearby compass needle. So, if you had a wire and you actually ran electric current through the wire, there would be a deflection of the compass needle. If you brought a compass by, you would find that that compass needle would deflect as you moved it all the way around the wire. And in fact, then you would conclude maybe that there was a magnetic field line circularly around this wire, because the compass would deflect in such a way as it moved it around the wire. Interesting. Andre Agassi Ampere suggested, I'm not sure about the middle name, Andre Ampere suggested that molecular current loops are responsible for all magnetic phenomena. So Ampere suggested that maybe, since moving current is producing a magnetic field, maybe that's what happens even on a small scale. And in fact, he was correct. That all magnetic phenomena, even on a small scale, originates from just, say, electrons moving around in the atom. That charge moving around the atom is your source of magnetic field. Joseph Henry demonstrated that a changing magnetic field produces an electric field. So if you have a magnetic field and you change it, either by moving it or change its orientation or somehow changing the magnetic field, you can generate an electric field and hence move electric charges based on that. James Clerk Maxwell theoretically showed that a changing electric field gives rise to a magnetic field. In theory, it was one of the most brilliant theoretical observations of all time. He came up with a theory showing that if you change the electric field, you get a magnetic field, and vice versa. He came up with all the electromagnetic theory in one class. magnetic field, you get an electric field. We're going to use that to our advantage because that would be the basis of power generation. That's how we're going to get electricity. It's by changing the magnetic field. Here are some experimental observations. A stationary charged particle does not interact with a static magnetic field. So if I had a magnetic field, I put a charged particle in there, nothing would happen if it were stationary. It's not changing. The electric field is not changing. Nothing happens. When moving through a magnetic field, a charged particle will then experience a force. So that charged particle is moving, has a velocity, and all of a sudden there will be a force on it, a magnetic force on it. That force is maximum when the particle moves perpendicular to the field, and zero, minimum, when the particle moves along the field line. So it actually has to move perpendicular to the field to get your maximum result. If it moves with the field lines, it's not experiencing a changing magnetic field. The force alters the direction of the particle, but not its speed. If the force is always perpendicular to the direction that it's going, then it may make it move in a circle, like a centripetal force, but it will never accelerate it in a forward direction or decelerate it in a forward direction. It won't change its speed because the force is always perpendicular to its current motion. And the force is proportional to the magnitudes of the velocity and the magnetic field respectively, and we designate magnetic field by B. So the magnetic field is designated by B field. Why B? I think it's because we haven't used B for anything. It's available. And we've used M for mass and magnitude and other things. And B kind of looks like an M. If you turn B on, you got M on its side, put a bar over it, it kind of looks like an M. So it makes sense. It's like a magnetic field. I wish I had a better explanation. Mathematically, all this is summarized as this. With all that experimental observations, we would say that the force on a charged particle moving in a magnetic field, designated by B, is equal to its charge times the cross product of its velocity with the magnetic field. The magnitude of this cross product is the charge times the magnitude of the velocity times the magnitude of the magnetic field times the sine of the angle between the velocity and the magnetic field. That's the magnitude of any cross product. Is the magnitude of the two vectors times the sine of the angle between them. And the direction is given by one version of the right-hand rule, which I'll show you in a moment. The direction will be given by the right-hand rule. The System International Unit for magnetic field is the Tesla, named after Tesla. Nikola. We did a lot of this stuff. So the force is perpendicular to both the velocity and the magnetic field, and this is how you would apply the right-hand rule. So it's a cross product, B cross B. You would take your right hand, you point in the direction of the first vector, and close it through the smallest angle you can towards the second vector. And your thumb points in the direction of the resulting vector. So the cross product of B cross B would be a force going perpendicular to that plane, upward in this case. It looks like this. That's about as best as I can draw with the cursor. That's your cross product. Right? Going in the direction of the first vector, close on the second, perpendicular to the plane. That's if your charge were positive. So that's the direction of your cross product, B cross B. If the charge were negative though, then you'd have to flip the opposite way. So you do the cross product, and then the force would be the opposite way if the charge were negative. All right? Kind of like Alabama. Oh. No. All has to do with the charge. We have electric forces, so electric forces go with the charge and the field. Electric forces, F equals QE. If the charge electric field goes along, the force goes along the same direction as the electric field. Force is parallel to the electric field. Magnetic force, the force is perpendicular to the magnetic field. So there's a difference. For electric force, the force would be independent of the velocity at that moment. Force equals, makes an acceleration in the forward or opposite direction, and doesn't depend on the value of the velocity at that moment. For a magnetic force, the force only exists if you have a velocity and it's proportional to that velocity. For electric field, the force changes the speed and kinetic energy of the particle, so it will change the magnitude of the velocity. If it's a magnetic force, it will not change the magnitude of the velocity, it will just change the direction of the velocity. So it won't change the speed or the kinetic energy of the particle, it'll just change its direction. It's a perpendicular force. So those are major differences in the way that we look at electric and magnetic forces. So let's try this out. A proton moves at 8 times 10 to the 6 meters per second along the x-axis, enters a region in which there is a magnetic field of 2.5 Tesla directed at an angle of 60 degrees with the x-axis aligned in the xy plane. So we have this electron, or proton, moving in the x direction with this velocity, and there's a magnetic field at a 60-degree angle going up like this. Calculate the initial force on and the acceleration of the proton. Now, even before we do anything, I could do the right-hand rule. The proton is a positive charge, and I would see, pointing in the x direction, closing out the B field, that the force is going to be out towards you in the positive z direction by the right-hand rule. The magnitude of that force would be QBV sine theta. Charge on a proton is 1.6 times 10 minus 19 coulombs. It was moving at 8 times 10 to the 6 meters per second. The magnitude of the field was 2.5 Tesla. And the angle between the velocity and the field, this angle right here, was 60 degrees. So we have sine 60. So that's 2.8 times 10 to the minus 12 newtons. And by the right-hand rule, the direction of the force would be in the positive z direction towards you. Acceleration would be force divided by the mass, 2.8 times 10 minus 12 newtons divided by the mass of a proton, 1.67 times 10 minus 27 kilograms. 1.7 times 10 to the 15 meters per second squared, which is a pretty large acceleration. Let's try another problem. A duck flying due north at 15 meters per second passes over Atlanta, where the Earth's magnetic field is 5 times 10 minus 5 Tesla, and is in a direction 60 degrees below the horizontal line running north and south. If the duck has a net positive charge of 0.04 microcoulombs, what is the magnetic force acting on it? So here we have a duck flying north-south. We're looking at the Earth from the side view. So there's Florida, there's the Yucatan Peninsula, South America, and there's Atlanta. So the duck is flying south to north. duck. See how well you did. Okay, blue eye. Flying south to north. Encounters the Earth's magnetic field. Earth's magnetic field is generally from south to north, but it's at Atlanta, it's directed 6 degrees down. So what's the magnetic force acting on the duck? Well, the force would be QBB sine theta, 0.04 times 10 to the minus 4 coulombs times 15 meters per second. That's a fast moving duck. Times 5 times 10 to the minus 5 Tesla. And the angle between the two is 60 degrees. Velocity in the magnetic field. So that has a force of 2.6 times 10 to the minus 11 newtons. What would the direction of that force be? This duck is flying from south to north. And we're looking at it from side view. The Earth's magnetic field is generally running south to north. Is that into the board? So
From B to B, right?
oh, from B to B, the direction of the force? Yes, from the right-hand rule. So we're pointing B, pulls on B, direction of this force would be into the page. And so as you were looking at it, it would be west. This duck is flying south to north. It would feel a little bit of force towards the west. Small force, 2.6 times 10 minus 11. Some people feel that this is how ducks know how to fly north. Or birds know how to fly north. That they're flying and they feel this little bit of they have a little charge in them, and so they feel this little bit of a push one way or the other as they're flying. I think the sun has a lot to do with it too. The sun's low on the horizon, that's probably south, and you go the opposite direction. That's probably north. Let's skip this one.
We should test the line though.
Yeah.
But if you like what you're talking about, that's something to do with North Star.
They test what?
They do a lot of tests, like
With night?
in different environments and stuff like that.
With the
It's
North
like
Star?
to do with North Star. They set them up in a room and they do one that didn't have a North Star set up. And it was and it did go right there, all of them, like something similar to North Star all of them.
These were bats or?
They did it with
Different-
different viruses and they did it with viruses.
Wow, that's pretty neat. That's pretty neat. You
It
can
was
find out
a
more
lot
about that.
of
I gotta find out more about that. Pretty cool. The North Star. Yeah, the North Star would be, I mean, if you were a natural creature, you would recognize North Star. That's one of the things you look at. But it's not the brightest star out there, but it is the one that doesn't move. That's pretty neat. One more thing before we go today. I want to introduce one more thing. Kind of along the same lines. Let's say I had a wire. I had these charges in a wire. And so these charges were moving in a wire. They have some kind of drift velocity and they're making their way through the wire. And I put this wire in a magnetic field so that all these individual charges are feeling a force on them as they move, according to what we just found out. Force equals QV cross B, or the magnitude QVB sine theta. So all these charges that are moving are going to feel a force, and collectively, that might be a significant force on the wire itself. So let's look at it this way. I have a bunch of charges moving to the right. Number of carriers is equal to the number of carriers per volume of this material times the actual volume of this segment of wire, which would be the volume of this cylinder, which will be the cross-sectional area times its length. So the total force on that segment of wire would equal the actual number of carriers in that segment, which is this number right here, the carriers per volume times the volume, times the force on each carrier, QVB sine theta as we just found. Number of carriers times force on one carrier. So I could write this. Well, realize that for check 27, though, the current flowing in this wire is equal to the number of carriers per volume for that material, little n, times the cross-sectional area, times the charge per carrier, times the drift velocity. So the current is n times A times Q times drift velocity. So I can rewrite this as force is equal to I times the length of the wire L times magnetic field B times the sine of the angle between the current direction and the magnetic field. ILB sine theta. Field of sine theta. Where theta is an angle between the current direction and the magnetic field. In general, this actually should be written as a cross product as well. Force is equal to I L cross B. And right-hand rule would apply. You would point your right hand in the direction of I, so the same right hand, close it in on B, and that would give you the direction of the force. And this one, you wouldn't have to worry about positive or negative, because if you have a current direction, that's the direction you're going with. So you just go in the direction of the current, you got your force on the segment of the wire. ILB sine theta. Let's try this out. The wire carries a current of 22 amps from east to west. Assume that at this location, the magnetic field of the Earth is horizontal and directed from south to north. And that has a magnitude of 0.5 times 10 minus 4 Tesla. Find the magnetic force on a 36-meter length of wire. How does this force change if the current runs west to east? So we're going to have a wire. We're just going to have it run 22 amps from east to west, horizontally, and see what the force is on the wire. Well, the magnetic field is going north, so there's an angle of 90 degrees between the two directions. The force would be ILB sine theta. 22 amps times 36 meters. Magnetic field of the Earth is 0.5 times 10 minus 4 Tesla. Sine of 90 degrees is 1. So this would have a force of 4 times 10 minus 2 newtons directed towards the Earth. So I have this wire horizontally above me in the Earth's magnetic field. And if I run that current, the wire will be forced downward towards the Earth. Kind of neat. What would happen if I ran the current? You can see that force downward by using the right-hand rule. Point in the direction of the current, close that magnetic field, you're going into the goal, which would be towards the Earth. That's what we're looking at top view. What would be the direction of this force if the current were running west to east? The opposite direction.
Get away from there.
You'd be away from the Earth, right? If we're going west to east, you point in the direction of the current, try to close on the B field if you can, and you'd be coming out towards you, away from the Earth, top field. Possibly, if the wire were light enough, you could run a current through this wire, and maybe the magnetic force, which is going away from the Earth, might be able to be enough to offset its own gravity, and hence the wire might float. Levitate. That'd be cool. If you run enough current and a light enough wire, you can make it levitate. Or maybe even move upward. What's that supposed to be? Has anybody done that before? Wow. How much time do we have? Are we near the end? Oh, I got it right there. I got enough time. I got 6 minutes. Has anybody done that before? Has anybody levitated stuff? Have you heard of Coral Castle down in Florida? Coral Castle? There's a place down in Florida, it's about 20 miles south of Miami. It's called Coral Castle. And it's a castle built out of huge blocks of coral. Some of these blocks of coral are 20 tons. Right? They were quarried out of the nearby coral, and they were built into this castle. And part of this castle, well, it was built by a guy named Ed Leeds-Skalnik, who was a Latvian immigrant at the turn of the century 100 years ago. Right, so in the early 1900s, he came to this country. The reason he came to this country was he was about to get married, and to his childhood sweetheart, I guess she was 16, and at the altar, she decided she didn't want to marry him. So he figured he needed to change scenery, so he got on a ship and came to America. And he spent the rest of his life building this coral castle in honor of his lost love. So he built this castle, and he also built a table that's heart-shaped. It's called the largest Valentine in the world. It's a multi-ton table made out of coral in the shape of a heart. And he had all sorts of astronomical devices. He had this moon that was perfectly aligned to the equinoxes. And he had this door, this 9-ton coral door that was so perfectly balanced that if you came up to this door and you hit it with your finger like that, the door would open. Perfectly balanced. Ed Leeds-Skalnik was 98 pounds. He weighed 98 pounds. And all he had was some kind of rudimentary pulley system. And when people look at his pulley system, they figure, how could he possibly move these 20-ton pieces of coral from place to place? He said that he had mastered the power of magnetic levitation. That he had found the inanimate charge found in everything, not necessarily conductors, but in every inanimate object. He was able to utilize his charge with the Earth's magnetic field. He said there was some kind of vortex there down in South Florida, near the Bermuda Triangle. There's a vortex of the Earth's magnetic field there, and he was able to utilize it to levitate stuff and move it from place to place. He said it was the secret of the pyramids. He had discovered the secret of how they built the pyramids. There are pyramids all over the world, right? So not just the Egyptian pyramids, but the Mayan pyramids and the Inca pyramids. They're on the top mountains. So he had found the secret of the pyramids. He'd only work at night. He worked alone. But there was one story that some teenagers went out there at night, saw him working, and they saw exactly that he would just kind of like directing things. Had one boulder and it would just kind of fly. In the early 1940s, they decided they had to put a highway through in that section. It was near Miami. And they said, you know what? Eminent domain, we're going right through your property. We got to move your coral castle. So he moved his coral castle. He had a friend who had a large flatbed truck. And he said, leave the truck here at 8 a.m., come back at noon. The guy left his truck there at 8 a.m., came back at noon, and it was hollowed up with blocks of coral. And moved it down to where it is now. Block by block, this whole coral castle, all of his monuments, table, everything, moved it to another location, rebuilt the whole castle. I've been there. I was there when I was 6 years old. I didn't know what it was. My family went there, and we paid admission. At that time, you could go all over the place. So I was a 6-year-old, and I was climbing up this coral castle, kicking in the coral and making footholds, you know. So probably if you see footholds along this castle, it's probably due to me, 6-year-old Dr. Golben. Climbing up this castle, probably destroyed the place. But it's there. Right? So I thought, I won't go over too much here, but something to investigate. I thought one of my life ambitions would be to figure out how we did it. And I think I figured out how to do it. So unfortunately, I already found that life ambition. I want you to think about it, and if you're interested, I'll give you the answer of what I think he did towards the end of this course. But he does have 3 papers that he found on the internet. He wrote 3 papers on magnetic currents, is what he called them. He wrote 3 papers. You can probably find it on the internet and download them. I've read those. I can't make heads or tails of them. I can't make any sense of them. Maybe you can. But look up Ed Leeds Scalman, Coral Castle, magnetic currents, and you can find those papers on the internet and see what you think. Okay, let's stop there.